A large chunk of the forces chapter is about using Newton's laws to explain motion, to explain what's happening. Newton's first law doesn't tend to get as much, often abbreviated instantly as N1, but remember, in kind of written descriptions you can't use abbreviations. But just to remind us, that's an object, right, any object will remain at rest or move at a constant speed in a straight line. We could just written in a constant velocity, because that includes the idea of constant speed and a straight line, unless there's an unbalanced force acting on it. So it tells us what happens if the forces are unbalanced, right? Something's going to change. It's either going to change speed or it's going to change direction. If it was at rest, it's going to start moving. The opposite is if the forces are balanced or if there's no force. It's just worthwhile clarifying that idea that those two are equivalent to each other. Balanced forces are equivalent to no force acting on an object. Newton's second law, though, is the one that we'll spend much more time on, but it's actually the simplest of the two. It's given in the formula sheet. It's written in the formula sheet as F equals ma, but I want to stress this idea of fun equals ma. It's the unbalanced force that's key. So for instance, in a car, it's not the engine force, it's the unbalanced force, which might be the engine force take away frictional forces. Right, or there might be aspects of gravitational forces involved if a car's going up or down a hill and so on. You've got to take account of all the forces. So the formula here is very simple. You've met it before, familiar with it. But a large chunk of this unit then is just practice at using this in different situations. So that even if a strange situation comes up in the final exam, you have a good idea of how to approach. And the basic idea of how to approach any problem involving force and acceleration, Newton's second law, is to draw a free body diagram. Don't spend ages making it look like the object you're interested in. A circle or a square will do. And then what we want are only the forces that are acting on that object. Right? No other objects involved. The only impact that they can have on the object that you're interested in is by applying a force, and therefore they would appear. So for example, if we look at a rocket taking off, we could have an arrow to represent the thrust. Now if you're doing these free body diagrams because the question has asked you specifically, then you should label that out in full. If you're just doing working for your own calculation, then a T would do. Notice we want the arrows to actually meet the objects and not just kind of floating in thin air beside them. The object, the rocket, would have weight pulling it down. Remember, it's not gravity. Right? Gravitational force would be acceptable. And possibly air resistance. Make sure my arrow touches the object. Except we'll see that in most examples we're going to neglect air resistance. And one way of getting around that is often in the questions you get things like at the moment of launch. Well, at the moment of launch the rocket isn't moving, so it doesn't have any air resistance at that point. And once again, only the thrust and the weight. So in general, drawing these diagrams is really important. Everything is only analysed in terms of the forces acting on it. And all the different examples, different situations we'll look at, they all come back to the same idea. Draw a diagram, and then beside that diagram, write what fun is in that specific situation. So to look at the most complex thing that we could get, if we included air resistance, that would be T because it's going up the way, minus W because it's going down, minus R because it's going downwards as well. And then we can use that along with the fact that fun equals ma to solve the problems. But this bit here, writing what fun is basically the key. I mean, plugging numbers into the formula fun equals ma is not difficult. But what is in the different questions is working out, well, what is fun in this particular situation? So if this was a rocket taking off like that, okay, and we'll look at some worked examples over the next few slides. Before we look at the worked examples, one other definition we need is the definition of the Newton. So using this formula, fun equals ma, we get the idea that 1 Newton of force, so 1 Newton is the force, and if you look at the right hand side of the formula, ma, which causes 1 kilogram to accelerate at 1 meter per second squared.